And happy Monday morning, everybody. I'm Jane Platt with NASA's Jet Propulsion Laboratory in Pasadena, California. Our topic today is NASA's Mars Curiosity rover, which is now at the base of Mount Sharp. It has done some very interesting science on the way there, and now it's doing even more at the base. We're going to have four brief presentations, and then we'll take questions from reporters. If you have a question, press star 1 to be placed in the lineup to ask a question. And the visuals that you can go to follow along with today's media telecon are at go.nasa.gov/curiositytelecon. That's go.nasa.gov/curiositytelecon. I'm going to quickly introduce today's speaker, and then we'll begin. The participants today are Michael Meyer, the Mars Exploration Program lead scientist from NASA headquarters in Washington; Sanjeev Gupta, a Curiosity Science team member from Imperial College London, who is speaking today from St. Olave's Grammar School. Then we'll have John Grotzinger, the Curiosity Project scientist from the California Institute of Technology in Pasadena; and Ashwin Vasavada, Curiosity Deputy Project Scientist from JPL. We're going to start this morning with Michael Meyer.
Well, thank you. The Curiosity rover was sent to Gale Crater, but why did we pick Gale Crater? There were signs of water in its past, flow features indicative of water, and minerals that formed in the presence of water. But the kicker was a huge mountain, Mount Sharp, in the middle of Gale Crater, about 3.5 miles high. This showed layers of different minerals that form in water, a promising record of the early history of Mars when the planet was warmer and wetter. Also, there's bonus science. Is the buried mystery how Mount Sharp formed? How did it form in the middle of the crater? Curiosity landed in Gale Crater on August 6, 2012, and immediately headed in the opposite direction to Mount Sharp. We headed at the junction of 3 different geological units. This proved to be a smart move. From the exploration of the area called Yellowknife Bay, we have concluded that the base of Gale Crater had the right ingredients and environment to have been able to support microbial life. But one big question remained: for how long? Now that we have had the opportunity to explore on our way to the base of Mount Sharp, the puzzle pieces are coming together, and we're now able to answer 2 big questions about Gale Crater. How did Mount Sharp form? And how long was there water to support microbial life? The answer, we can see image 2. Gale Crater had a large lake filling the bottom of the 96-mile across crater, perhaps even a series of lakes. This lake was large enough it could have lasted millions of years. Sufficient time for life to get started and thrive. Sufficient time for lake sediments to build up to form Mount Sharp. So now, to give us the details on the pieces of this puzzle, I turn the mic over to Sanjeev Gupta.
Thank you, Michael. So I'm sure we've all done jigsaw puzzles in our lifetime. So reconstructing the ancient environments and landscapes of Mars is a little bit like piecing together a jigsaw puzzle, but without actually knowing what the final puzzle picture is. In our long drive from Yellowknife Bay to where we currently sit at the foot of Mount Sharp at Pahrump Hills, the science team have been examining a whole series of different types of rocks, trying to pull these together to build that picture of the overall setting of Gale Crater. And we're now in a position that the jigsaw picture is actually coming into view. It's not the complete picture, what we're able to start seeing the overall setting. So firstly, as we were driving from Yellowknife Bay towards Pahrump Hills, we encountered a lot of conglomerates, that's pebble beds and sandstones that we consider were deposited in ancient river environments. But then when we got to Kimberley, the site Kimberley in Gupta figure 1, you can see we found an extremely interesting new rock type that we could observe in the rover, in the orbital images, and these had a stripy appearance. Now, if you turn to Gupta figure 2, you can see some of these rocks, and I'm going to lead you through a whole series of these spectacular images that the Curiosity's Marscam cameras have taken. In Gupta figure 2, you can see beds, sediment beds of sandstones that are inclined. So if you look in the middle ground of this picture and you put a scale there, you can see beds that are inclined to the right-hand side. That's towards the south. That's towards Mount Sharp. And basically, these beds are recording build-out of sediment, accretion of sediment towards the south. Now let's look at it from another direction. If we go to Gupta figure 3, this is a view of our spectacular site at Kimberley, and this is just a beautiful picture. We're here looking south, actually looking in the direction of Mount Sharp, and we can see a whole series of beds of sandstones with some pebble beds in there that are actually inclined on a large scale towards the south. So again, we're seeing a systematic inclination of sediment beds to the south, and this is recording build out of these sediments to the south. And we always see this systematic pattern, which is quite intriguing. Let's take a side-on view of this. So if you turn to Gupta figure 4, this is looking side-on, looking towards the west at Kimberley, another spectacular mosaic. Mount Sharp, actually, you can see it in the distance on the top left-hand corner of this mosaic, and it lies to the south here, and we're looking west. And again, in the foreground, we can see these prominent south-dipping beds, south-inclined beds, recording migration of depositional systems to the south. And then in the distance, in the background, you can see sediment beds that are horizontal, that are flat-lying, overlying these inclined beds. Now, we believe that those horizontal beds represent ancient river deposits, but what do these inclined beds represent? They're quite intriguing. Now, we have our answers, or we can help explain this by looking at analogs on Earth. And one of the key places that we find such inclined beds is actually at the mouths of river channels where they feed into lakes. So what happens at where rivers actually feed into lakes? And we're trying to build this evidence. So if you turn to Gupta figure 5, you can see a cartoon that we've prepared that just illustrates this schematically. On the right-hand side in green, you can see rivers traversing a landscape, building up river deposits. And then on the left-hand side, we've got in blue a lake, a standing body of water. And when rivers encounter a lake, the water in the river channel that's carrying sediment it suddenly decelerates. Basically, it's hitting a standing body of water and the velocity decreases, and suddenly all the sediment that's being carried in the river channels abruptly deposits. And what this leads to is basically deposition of an inclined sediment bed dependent on the water depth in the lake. And through time, as that river channel and the delta extends lakewards, we see those inclined beds basically build out and accrete. So this is really exciting because we believe we have clear evidence of build out of sediment beds in this inclined pattern, which suggests former deltas. And these are likely to be quite small, maybe a couple of meters water depth, so very, very small deltas, but certainly clear evidence that we're building out into likely into a standing body of water. Now, as we've been exploring, we've been able to track these deposits very nicely. And what's amazing is that we don't just see them in one place. We can see them over several kilometers distance, both laterally and also traced towards Mount Sharp. But what's very interesting as we trace them towards Mount Sharp to the south is that these inclined beds actually rise in elevation. We see them at different elevations. So if you turn to Gupta slide 6, this is actually a slide from an image, again, looking to the west with Mount Sharp to our left-hand side there. And in the middle ground of this image, you can again see these large-scale inclined beds, inclined again, as we've seen systematically to the south. But this outcrop that we're looking at is actually something like 25 meters higher in elevation than the rocks we were seeing at Kimberley. So what we're probably looking at is another cycle of delta migration. So we believe what we're seeing is multiple cycles of delta migration interspersed between river deposits and probably desert dune deposits, creating quite a complex collage of ancient environments. In Gupta figure 7, I've got a very schematic cartoon. This is very, very schematic, just illustrating this idea. So in green in this image, we have river deposits. The brown represent ancient delta deposits, and the yellow represent lake deposits. And what you can see is in the delta deposits, the inclinations representing migration of the delta in a single cycle, but what we have here is multiple cycles. So we've got 3 different cycles of delta growth and migration to the south. And what this section is looking at, this cartoon is representing in the vertical, is not only the growth of these deltas towards Mount Sharp as sediments were fed from the crater rim, but also that each delta is actually becoming younger through time, so that we're seeing an age progression. Now, what I've shown you is the deposits, the delta deposits and the river deposits. I'm going to turn over to John now because we made a prediction, the science team made a prediction as to what we would find as we went further south, and John's going to talk about those exciting results. John.
Thanks very much, Sanjeev. What I would like to do is now to build on what Sanjeev was saying by referring back to his image number 5, which shows in that predictive model that after the inclined bedding of the deltas, that if you do move laterally into a body of standing water, the layering or the bedding flattens out again. So that will figure prominently in what I'm going to be talking about. And it comes as a consequence of the science team developing a hypothesis that we're talking about here today. And that hypothesis makes particular predictions of things that we're looking for with curiosity. And so when we cross the boundary from the plains that Curiosity had been driving across, and we got to the rock that allowed us to say that we were at the base of Mount Sharp, that transition was really a key point for us. And that's what I'd like to now talk about a little bit. So if you then go to Gupta 7, you can see that the yellow color rock material, what's called lake deposit, the prediction would be if we drove the rover from an area of one of the brown patches where we have the inclined bedding that represents a delta, and we go further to the south, we might see the kind of deposits that would be consistent with a lake. And so we drove the rover across the boundary, the big boundary that we saw from orbit, from the plains of Gale Crater to the foothills of Mount Sharp, and in doing so, we went into what we call the Murray Formation, that we now believe, the first sample of which at Pahrump Hills is telling us that we may well have lake deposits there. So what do these look like? Well, if you go down to Grotzinger 1, what you can see is a new rock type that we had not observed before out on the plains. The top of this hill that Curiosity drove down from has the typical dark gray, massive-looking cross-bedded rocks that we have seen for years now on the mission, very typical. Those are the kind of rocks that were doing the damage to the wheels. And as we went down into the valley, now you can see something that looks very thin-bedded, very rhythmic, and there's no evidence for strong currents involved in the deposition of this sediment. So this is consistent with the prediction that as you go from a delta, if a river is debouching into a body of standing water, as Sanjeev mentioned, the momentum of that river moving along is dissipated, and the sediment that the river is carrying will just rain out onto the floor of what would be interpreted to be the lake. And we think that's what we're seeing here. Our lake floor deposits, very rhythmic in nature, is also interesting because it has the science team wondering maybe is there some daily cyclicity here, maybe yearly cyclicity. There's going to be a story in there in terms of what these very even bands might tell us about the ancient climate of Mars. Okay, now if you go to Grotzinger 2, here Curiosity has driven even further down the outcrop in the Pahrump area, and we believe this suggests that it's possibly maybe a more distal environment out within a lake. And so out in front of the delta, we get centimeter scale bedding, and maybe even further out in front of the delta, we get millimeter scale banding. And notice the change in scale between Grotzinger 1 and Grotzinger 2. So we have to put this together, this inference, using a principle that we use based on Earth geology called Walther's Law, where we take the vertical sequence of different kinds of rocks and relate them back to how they might originally have been deposited. But again, the very, very even bedding, no evidence for currents, and we think this was perhaps in a deeper part of the lake. Okay, now Grotzinger 3 tells us a very different story about what this ancient environment might have looked like. Because here we now see a feature called cross-bedding, well known to geologists. And what you're seeing is evidence that at one point in this environment, small waves of sand might have been migrating along. And in this particular case, we think that this was underwater. And these waves of sand, they might have looked like small dunes. One passes the other, and they preserve the fronts of the dunes preferentially well. And so what you see here is evidence for currents directed towards Mount Sharp. And again, consistent with the story that Sanjeev was telling us, we don't know whether this is an ancient river deposit, whether the lake level dropped and the rivers flowed out over once was the lake floor, or whether this was the kind of flow that went down the front of the delta and was entirely subaqueous in origin. But again, what we see is not only the stratigraphic evidence for the big inclined beds indicating sediments moving in the direction of Mount Sharp, but now we see the construction of ancient flows moving in the direction of Mount Sharp, and this paradox about how the Rover drives uphill and yet the water keeps flowing to the south is what allows us as a team to postulate the hypothesis that Mount Sharp wasn't there at the time that these sediments were accumulating. Okay, now one last Molly image of these fine sediments that are not cross-bedded. We see a lot of mudstones. Again, what you would predict to be out in a lake environment would be the finest grain fraction of the sediment, and we do in fact see a lot of very, very fine grained sediment. Here's a bedding plane view that's been cleaned off by our dust removal tool that shows some beautiful early diagenetic features of crystals that were growing in the mud at the time. And these crystal molds are very similar to things that we see on Earth associated with bodies of water that eventually dry up. So this is an indicator to us that the salts that might have been dissolved in the ancient lake water or in the pore water associated with the sediments, as it evaporated, it concentrated those salts and they precipitated out to form these crystal-like features. We don't know what their composition is yet, but as we do more work in the Pahrump outcrop, including drilling, we hope to get some more information on this. Okay, so what does this all mean? So, this is something that the science team has been after since the day the landing site was selected. We really wanted to know what these ancient environments look like. If you take everything that Sanjeev and I put together and look at Grotzinger number 5, what you see are a series of panels. And it's a view that we imagine might have been towards the crater rim. Possibly it was cold enough that if water was stable, it might have been present as snow or ice up in the hills of the crater rim. And then during wet periods, maybe it melts or it's supplemented by groundwater. We don't really know for sure, but we know that water flows across a series of alluvial fans, and as Sanjeev said, those alluvial fans stack one on top of each other. There's not just one of them, there's a whole stack of them. And then out in front, you have a body of water, and then notice in the third panel, once that water stops flowing, the sediment that the water was transporting has piled up. And so in this manner, the crater gets filled in with a series of delta, alluvial fan, and lake deposits, which now brings me to Grotzinger 6. And what we can see there now is maybe a suggestion about how the riddle of Mount Sharp was formed. We see a crater basin. The yellow represents sediments derived from the crater rim, maybe in alluvial fans when water was flowing. And the brown represents lenses of what might have been ancient lake deposits. And what we're trying to show in this cartoon on the left side is that there's a whole bunch of these. We don't imagine that this environment was just a single lake that stood for millions of years, but rather a system of alluvial fans, deltas, and lakes and dry deserts that alternated probably for millions, if not tens of millions of years as a connected system. And then on the right, this shows basically what we have at the time that the Murray Formation may have formed, and perhaps some of the other Gale units, that after they were deposited, they were then eroded, we presume, by the wind, and to a small mound. Now, this is not meant to represent the Gale mound that exists today, that represents all of Mount Sharp. We actually are beginning to think that maybe Mount Sharp formed in a series of episodes involving sedimentation and erosion stacked by different processes. But the point is, on the right-hand side, Curiosity landed down on the yellow, close to the gray line that makes the circle, and that gray line might have been a little taste of a lake deposit that we saw down in Yellowknife Bay. But then as we drove the rover to the south and uphill, paradoxically, is where we were able to discover the bigger lake complex represented by that first dark brown band. So this shows you how you can use geology as a way to reconstruct ancient environments. And with that, I'll turn it over to Ashwin to tell you about what all this means from a climatic point of view.
Okay. Yeah, so as you can hear, as you've heard actually, the year we spent traversing from Yellowknife Bay to the foot of Mount Sharp was really productive. Even though we had our foot on the gas, we kept looking out the windshield and built up this incredible record of clues as to, not only what happened with Gale Crater 3.5–4 billion years ago, but Mount Sharp itself. And I'll tell you a little bit about the implications of that for the ancient climate and our ability to even understand and model that climate in a way that could have been capable of producing the features that we see geologically. So as a reminder, of course, today Mars' surface is shaped by wind and sand and dust. It's dry, and it's probably been that way for about 2 billion years. But as you heard today, Mars was once a planet shaped by water. Landscapes from that time are like relics today. They're out of place, unexplained by the current climate, and need to be explained. The landscapes of Mount Sharp indicate that rivers, lakes, and groundwater were present over millions of years, something that would be impossible on Mars today. If our model for the formation of Mount Sharp is correct, it implies that the ancient climate of Mars was different from today's climate in 3 key ways. First, the atmosphere must have been thicker. Without a thicker atmosphere, water would exist only as a solid or gas, not as a liquid. This isn't a question of temperature, but of barometric pressure. There's strong evidence, including from Curiosity, that Mars did indeed have a thicker atmosphere. In fact, it's likely the atmosphere was several times more massive than at present. Second, the atmosphere must have been, Mars must have been warmer. To have liquid water running in rivers at Gale Crater and elsewhere on Mars requires temperatures above freezing over much of the planet. This turns out to be harder to explain. Even with a thicker atmosphere of carbon dioxide and other greenhouse gases like water, sulfur dioxide, or hydrogen, it's difficult in models to raise global temperatures enough. But unless you do so, any liquid water would quickly freeze. Third, the climate system must have been loaded with water. Today, nearly all of Mars' water is frozen around the poles. Even if the atmosphere were thicker and warmer, any water would still prefer to be frozen around the poles, leaving the atmosphere dry and causing a lake within Gale Crater to quickly evaporate. To get a long-lived lake in Gale Crater, there must have been so much water in the climate system that the frozen latitudes were essentially filled up, and water was forced to warmer latitudes where it would exist as liquid. This is a critical point. To sustain a lake at Gale Crater for millions of years, Mars would need a vigorous hydrological cycle to keep the atmosphere humid. The humidity could be explained by expanses of warmer ice at lower latitudes, or even better, by expanses of liquid water, like an ocean. A humid atmosphere would slow the evaporation of Gale Lake and also resupply water through precipitation. In Vasavada 1, which is a repeat of the figure Michael Meyer showed earlier, you can see an illustration of what Gale Crater may have looked like when Mars had a thicker, warmer, and more humid atmosphere. In this graphic, precipitation in the form of snow on the crater rim is melting and supplying liquid water to streams that flow into the crater lake. It's important to keep in mind that models that predict the climate on Mars are full of uncertainties, just like they are for Earth. Constructing a model of Mars' ancient climate that was thick, warm, and humid for millions of years has proven pretty challenging. However, it's possible that such a model may not be necessary, Maybe what we see can be explained as a result of shorter-lived warm and wet climates, created either by volcanism, orbital changes, large asteroid impacts, all of which were active at the time when Mount Sharp was forming. Each event may have created warm and wet conditions for hundreds or maybe thousands of years, perhaps enough to fill Gale Crater with one more layer of sediment. As we continue studying Mount Sharp, one question we'll ask is whether temporary climate fluctuations could form what we see geologically, or whether a long-lived warm climate was truly necessary. So, in summary, what we described here today is powerful new evidence for long-lived liquid water in Gale Crater. What's new with Curiosity is that this evidence is from close-up studies of the sediments carried by the water, and in that respect, provides more clues than the existing wealth of evidence for early wet Mars based on only studying landforms from orbit, like the valley networks on Mars Highlands. Recent studies of all these data tend to push warm and wet Mars a little later in its history than we previously thought, to about 3.5 billion years ago. Therefore, it also extends the time over which potentially habitable environments may have been present. And with that, turn it back over to Jane.
Okay, thank you very much to all our speakers, and we're going to begin the Q&A portion. So reporters out there, if you have a question, please press *1 and the operator will put you in the queue. Again, we do have quite a few people online with us today, so I'd like to ask everyone to limit, at least on the first round, one question and, if necessary, one follow-up, so everybody gets a crack at the first round. All right, our first question will come from Alan Boyle at NBC News. Hi, Alan.
Hi. Just a real quickie and then a little bit following up on what Ashwin was saying. Is this being published anywhere? Is there a reason why you're talking about this right now? And I guess the bigger question would go to that idea of episodic presence of water, that other researchers have said water probably existed but for very short periods of time, and it sounds as if, from what Ashwin was saying, that might be consistent with what you're seeing. Maybe you could discuss that a little bit more. Thank you.
Hi, Alan. John Grotzinger here. I'll address the first part and then turn it over to Ashwin for the second part. No, we don't, in fact, have a manuscript prepared on this yet. We will begin work on it soon. One of the things that we're trying to do at this point in the mission is to share the results that we get in a more raw, more immediate form with the public, with the understanding that the journals support this kind of activity, and we think it's fun for the public to see these as hypotheses that we'll test as we go along.
In terms of the short-lived versus longer-lived climates, and this is Ashwin, of course, that is one of the most interesting areas of Mars paleoclimate research at this point. People are looking at various landforms on Mars, mostly the valley networks, these many hundreds of incised channels into the Mars northern highlands, trying to understand geologically how long did they flow, how much water did they carry, whether they may appear to terminate into a standing body of water that could have filled a large part of the northern part of Mars. All these things are pretty actively worked on, and our data will will allow another very close-up, different kind of study from the sedimentology to understand those same questions. I think at this point the jury is out. There seem to be reasonable explanations for either forming these features by a series of short-lived episodes or a sustained warmer climate, but we'll be able to add to that with the evidence that we find in our study of Mount Sharp.
Thank you.
Okay. The next question will come from Elizabeth Howell at Air and Space Magazine.
Hello. I was wondering about the status of ChemCam. There was some mechanical difficulties expressed in a press release recently, so how is it doing?
ChemCam is back in business, but having to modify how they operate the instrument to account for the fact that their focusing laser has been losing power in the last few operations, and maybe at the end of its life. And this is a secondary laser on ChemCam that's used to put a little beam on the target and then focus the telescope for the main laser to then follow up with the spectroscopy. There are ways they think they can operate ChemCam just using the main laser and having other ways of focusing the telescope that don't involve that guide laser. So right now it's a little bit slower operations with ChemCam as they work through those alternatives, but otherwise the instrument's doing great, and we'll be expecting to continue to use it.
Thanks. Our next question is from USA Today and Tracy Watson.
Hi, Dr. Glossiter, I would wonder if you could go over again the evidence that Mount Sharp was not there originally. I'm afraid I didn't quite follow it. That'd be great. Thanks.
Sure. The one thing to start off with, the one thing that we're not certain to how to deal with is the fact that there could have been a central peak that was left over from the crater forming its event itself. That peak might have been on the order of the elevation at which Curiosity is today, but we're not certain about that. So it is possible that there was an island in the middle of this large body of water that we've shown here. But the evidence all fits together. It could only have been obtained by driving the vehicle the way that we did for the length of time that we did over the terrain that we did. And there are a couple of things that fall out of that. The first is, since the day we left Yellowknife Bay, Curiosity has been continuously driving uphill. The second point is that Curiosity has been mostly driving with a direction towards the south. It's been net southwest, but we've always had a component of to the south. So the resultant is that we have been driving steadily uphill in a southerly direction. And we see evidence for flowing water in the rocks that we drive along, but the indicators that Sanjeev showed and that what I showed indicates that the inclination of the strata is to the south. And so there's a certain paradox, which is that, let's say, for example, Mount Sharp had been there and water was flowing off of Mount Sharp, then the water would be flowing downhill and it would also be going to the north. But the problem is that the way, when we look at the rocks that are exposed, we see the water flowing to the south. And so the resolution of the paradox is to acknowledge that the layers represent a time when water was flowing from the crater rim towards the crater interior, and it filled up a series of stacks, and then subsequently those stacks of layers were eroded, and so we drive uphill into younger layers of rock, and those younger layers of rock record the flow of water to the south. So that's the reason that we don't believe that there was a mountain in the way at the time that these sediments were being deposited.
Okay, thanks. And the crater forming event that you referenced earlier was an asteroid hit, presumably?
That's right.
Okay, thank you.
Okay, the next question is from Irene Klotz at Discovery Channel.
Thanks, Jane. I have two questions. The first is probably for John. Can you give us some sense of the amount of data that's been collected to get to this assessment, just as far as number of observations and if it was all done with what instruments were kind of key to it? And then the second question is for Ashwin. You mentioned about the possibility of an ocean to explain a more humid environment. Is there any physical evidence on Mars for an ancient ocean? Thanks.
Yeah, hi, Irene. The first part, it is, as you know, we built Curiosity to have an integrated payload that would all work together. A lot of the stuff that we showed you today is based on the imaging that comes from the mass cams and the mollies and the engineering cameras. And I think in months to come, you're going to get to see more updates in terms of the chemistry and the mineralogy that we've discovered as well. So but in terms of, you know, the geological framework does come from integrating all those observations, and in order to do that, the point that we like to make is that since the day we landed, we have drilled 5 5 samples. We've recovered several dozen of chemical analyses from the ChemIn and the SAM instruments. We've gotten hundreds of APXS analyses, thousands of ChemCam analyses, and literally millions of data points about the environmental sensing. And so when you collect a data set as large as that, you never know which ones are going to turn out to be the most valuable. And for us, really, I have to tell you, this was a complete surprise. There was no way to have recognized this from orbit, and it took the mass cams imaging as we drove along. All that driving we did really paid off for science. It didn't just get us to Mount Sharp, it gave us the context to appreciate Mount Sharp.
In terms of evidence for the Northern Ocean, this is Ashwin. It's a fascinating area of research that's gone on for a few decades, all the way back from Viking data. And the bottom line is that there's no smoking gun for an ocean in the Northern Hemisphere. There is a large, low topography, giant basin that forms the Northern Hemisphere, and a lot of the valley networks, these channels that are cut into the highlands, tend to flow downhill towards that large basin. People have been looking for definitive things like shorelines in the geology, but unfortunately, a lot of that, of those kind of more definitive features have probably been eroded away over time. So instead, there's a lot of little bits and pieces that are being put together by those who are studying the possibility of a Northern Ocean, including looking at where the valley networks terminate. But I think one interesting piece that will contribute here is other than the geologic evidence, there's a way to infer an ocean from the climatology. As I was talking about, if we require precipitation at Gale Crater over a long period of time, if we have a long-standing lake for millions of years, the atmospheric humidity practically requires a standing body of water like an ocean to keep Gale from evaporating and to keep a vigorous hydrological cycle going. So we'll continue to look at that and add to that pretty intriguing question.
Okay, we're going to move on to a question from New Scientist and Lisa Grossman.
Hi there. I wanted to ask a follow-up from John about, you said that this was a total surprise, that I guess what was the surprising thing about this? Because I remember talking about the possibility that Gale Crater could have been a lake and then Mount Sharp was deposited out of that lake, and then the rest of the crater eroded away from it. So what is new here that hadn't been suspected before, and what is the most surprising feature of it?
Yeah, hi Lisa, it's John. You're quite right. The fact that one might have intuited that there could have been a lake at present at Gale Crater is not a new idea. Indeed, that's the reason the landing site was selected. What is new is the way that we deduced its presence by using rover-based observations. And what Sanjeev talked about, really I can't underscore that enough, is the fact that we can actually see inclined strata on Mars is, to the geologists on the mission with experience in sedimentary geology, is something that we had really, that's the cutting edge for trying to understand the Earth. And basically, when oil companies collect seismic surveys across places, they are looking for inclined strata, because inclined strata is the way that you then get geometry that tells you where the rocks are that you're looking for. And so for us, when we saw the inclined strata and they were dipping towards Mount Sharp, that was really a great surprise. And it's hard, even on Earth, to arrive at flat layers like the type that I showed in my part and say, oh yeah, that's evidence for a lake, because it can be a non-unique interpretation. So finding the inclined strata was the big surprise.
Great, thank you.
Okay, next we're going to go to the BBC, John Amos. Hi, John.
Hi, Jane. A couple of my questions have been asked by others, so let me ask this: how do you test this going forward? What do you expect to see as you climb the mountain? If this hypothesis is correct, you feel as though you've nailed it. What would you expect to see as you went higher and higher, and you got into some of the sediments that come from a drier time in Mars history?
Yeah, hi, John. John Grotzinger here. That's in fact the fun that we're looking forward to next, and you know, who knows what the next couple of years are going to hold for us. But what we are going to do is look for evidence that we go from layers that indicate this beautiful, very fine, almost pinstripe-like lamination that's very even, that might indicate settling from suspension. And then as we work up through the outcrops, and as the rover, over the next 500 meters to a kilometer of driving, we're going to keep our wheels on the Murray Formation and try to look for an episodicity in the water coming and going, because we do see the evidence that's coming from the textures and also now the geochemistry, which indicate the concentration of salts. And so we'd like to see if there are times when the lake freshens, if there are times when the lake becomes salty, if there's times when it evaporates completely and leaves behind aeolian sand dune deposits. And that will really begin to tell us about the climate history of Mars at a higher level of resolution.
If I can add to that, I mean, one thing we would expect is that we would see repeated patterns. So as we go further south and higher in the section, if our model is correct, we should see more evidence of lake deposits with deltas and fluvial deposits, river deposits coming across the top of them. So let's see if we have multiple cycles of these developed in the section.
But as you go higher, you would expect to see more salts, yeah?
Kind of depends on what the lake is doing. So as we go basinwards into the lake, it sort of depends on what the climate does. So again, there's not only the sedimentary systems that are behaving, that are supplying sediment from the crater rim, but also the climate may be changing through time, and that changes the chemistry of the lake waters. So you can go from fresh waters into saline waters. So there's a temporal constraint there in terms of climate, and also the physical in terms of what's happening in terms of the dynamic environments.
John, the last thing I would add, just because it is an important point, is that as the chemistry changes, its redox may also change, and maybe it goes from being more oxidizing to less oxidizing or reducing. And so as we're hoping to find a diversity of presentations of different environments that we can drill and learn about habitable environments and also the preservation of carbon.
Okay.
All right, thanks. Our next question is from Nature Magazine, Alexandra Whitsey.
Yes, hi. I just wanted to ask when you're next planning to drill.
We've just completed a really wonderful study of this first maybe 30 vertical feet of Mount Sharp at the site we call Prump Hills, where we spent a couple weeks doing a reconnaissance campaign with our remote science instruments, ChemCam and the MassCam. Went back after looking systematically at the whole outcrop and the data covered by that first pass. We then circled back and looked in detail with our contact science instruments, our arm-mounted spectrometer, and our hand lens imager. And then our goal was to then look at that combined data set of the chemistry and the textures and choose a couple of key sites for drilling. And we're right at that point. And in fact, science team has just been discussing Friday and today where our first drill target will be for this Prump Hills outcrop. Actually, it'd be our second target, since the first thing we did after arriving here was drill Confidence Hills. But we'll probably drill our next target in the next few weeks.
Thanks, Ashwin. And the next question comes from Eric Hand at Science Magazine.
Hi, thanks for doing this. My question is for Ashwin about the timing and duration of this wet period on Mars. So you mentioned that you can now revise this wet period to maybe have been a little bit later in Mars's history, or that it was a little bit younger, 3.5 billion years ago. What was the previous best estimate for this wet period? And how did you revise it to 3.5 billion years? And then also a second question about the duration of this period. I think I'm hearing you saying that this wet period could have lasted on the order of millions of years, maybe even tens of millions of years. Is that just for the three wedges that you've seen so far, and could that wet period be longer if, as you drive up the mountain, you find more of this more of these wedges and more of these cycles? Thanks.
Yeah, the timing of when Mars was wet and possibly warm and wet has been evolving a little bit. It used to be kind of a canonical idea that it was the Noachian, the earliest billion years of Mars. That's when Chrism, for example, has found and Omega have found all the evidence of clays in the surface materials. I think the more that we study Gale Crater and then also the valley networks, we're realizing that a lot of that wet period was probably more like 3.8, 3.6, 3.5 billion years ago. So when I say 3.5, it's plus or minus a few hundred million years. But it's more towards the Noachian-Hesperian boundary. And with Gale in particular, Gale Crater is thought to have formed only at about 3.8 billion years ago. And so, we figure that a lot of this action was happening pretty soon after that, but extended over a few hundred million years. The geology that we see, when you just use very simple ideas of how long it might take to lay down these sediments, any one of these minor outcrops that we've shown may not have required more than hundreds or thousands of years, but the whole stack of the hundreds of meters of Murray Formation, in that simple accounting, we think may have taken millions or tens of millions of years. The part that we're not sure of is whether it was continuous or episodic, whether it was dry periods, etc., which is the same discussion that's happening in other parts of the planet too. Did you need a long-lived climate, or could short-term warm and wet periods account for what we see? And so that's what we'll continue to try to figure out.
But do you see the complete stack now, or is there the possibility that you'll see more cycles as you drive up and that it could be even longer than 10 million years?
So the 10 million years is assuming what we see now, we continue to see as we go through the rest of the Murray Formation, but that's even still just a few first 100 meters of Mount Sharp. What's above that, we'll have to wait and see when we get up there.
Okay, we've got a couple of additional media calls, and before we do that, it seems like a good time to jump in with a question that came in via Twitter from Emily Lakdawala at the Planetary Society. And her question is, are there any plans to couple these stratigraphic studies with geochemical and mineralogical data?
Yeah, it's John. Yes, they're intimately interrelated, and the strategy that we've got now for Operation Pahrump is going to be something that will apply through the rest of the mission, and it's not something that we've done with rovers before on Mars. For the Pahrump outcrop, we have planned a series of 3 loops, and in the first loop we do a lot of imaging and remote sensing with ChemCam, and then based on the integration of the remote sensing data is where we pick targets for contact science. And then we drive the rover to these locations and get the arm out and get detailed MOLI and APXS information. And then based on that, in the third loop, we come back and then we make a decision based on integration of all the geological, geochemical, and mineralogical information, what we're going to drill. And that's why we actually did the first drill as soon as we got there, to have a very broad brush view of what we might be dealing with mineralogically as seen by Kemen and Sam. So it's very much integrated.
Okay, and we're going to take a couple of more questions, and then if anybody, I'll do sort of a last call. So if anyone has already asked a question and wants to come back, we'll try to get a few more in if possible, if time allows. But right now we're going to jump over to Ken Kramer at America Space for a question. Ken?
All right, thanks for taking my question and for doing this. Can you guys estimate, please, the depth of the lake? I'm not sure you mentioned it before, and the total buildup time for Mount Sharp. And also, if I'm understanding this correctly, the sediments that built up Mount Sharp, these have come primarily from the crater rim then. Would it ever be worth sending some type of a rover there to do an investigation to get some more data on this? Thanks.
Sanjeev, you want to jump in and take a stab at that one?
So estimating the lake depth. So actually the inclined bedding is really helpful to us because that actually, the height of the inclined beds actually tells us the water depth at the time of formation. So actually these lakes were probably quite shallow. The inclinations have heights of several meters, a couple of meters. So what's actually happening is that you have shallow lakes, few meters, maybe deepening further to the south. We can tell this water depth from where we have the inclinations. But through time, the lake deposits get stacked up as you have multiple cycles of delta growth into a lake, deltas receding and the deltas growing out. So what you're actually building up is the lakes existing in time, maybe episodically, but existing in time for long periods, but not necessarily an extremely deep lake. So it's not necessarily Lake Baikal, hundreds of meters deep. But this is actually a hard problem. In fact, on Earth, what we do is we actually look at fossils and organisms to work out lake depths. Obviously, if we had that, it would be wonderful on Mars already. In fact, this is why actually looking at the sediments, the coarse-grained sediments, the sandstones and pebble beds, and these inclinations has been really helpful to getting a snapshot of that lake depth. John, do you want to add to that?
Yeah, I'll just say, Sanjeev, we do have a part of Earth history where we don't have all those organisms to help, and for the first 4/5 of Earth history, the way that we recognize lake deposits is almost exclusively from understanding the stratigraphic geometry of the deposits and also looking for sedimentary structures that indicate what current regimes were. So we're doing exactly the same thing on Mars as we do on the early Earth. It's rather remarkable.
Okay, we're going to take our next question from Leo Enright at Irish Television.
Thanks very much, Jane, and thanks to everyone for doing this. I'm very struck by those gorgeous thin-bedded sediments in Grotzinger 1. And I was just wondering, are these exactly the sort of sediments where you'd hope to identify preservation of organics, or am I oversimplifying things? My other thought was that this image seems to be, it's Hidden Valley as I understand it, so it must have been out of reach. And I'm wondering, are you satisfied that you can get to that particular epoch and do some of that geochemistry that Emily was talking about?
Yes, Leo, it's John here. Good question. That first image, actually, we saw very similar things, in fact, identical things at Hidden Valley that we were not able to work in with the rover, and so we pulled out and we went into Armagosa Valley, which is where this image is from. And that did two things for us. It told us that what we saw at Hidden Valley was not the exception because we saw it again, and that's always reassuring to see a common motif. And yes, either Grotzinger 1 or Grotzinger 2 would be the kind of rock where, from a primary concentration point of view, that would be viewed as an attractive candidate for drilling. But let me remind, I know I've been saying this for years, but the preservation thing depends on having an initial concentration of organic carbon, then that the diagenesis, the geochemistry that happens when you convert sediment to rock, is a favorable event, and then it depends on how long the rock has been lying around on the surface getting zapped with cosmic radiation. And all three of those things have to go our way for us to be able to make a discovery. So, but nevertheless, based on its physical features, this would be an attractive thing for us. For the unit Grotzinger 1, for that particular centimeter-scaled stuff, that outcrops at the tops of the valleys, and so we'd really have to scratch and claw our way up there to get to that. So we're hoping for one of two things to happen. Either our future traverse takes us uphill in a way that we might be able to intercept that with less risk to the vehicle, or that a block of it rolls down the hill where we can be confident that it's the same thing, and then we might be able to drill it that way. But we would love to have a go at some of this stuff.
Okay, I'm going to do a very last call, so if there are any more questions, press *1 right away, and we try to take a couple more. But in the meantime, we've got a question, again, from Irene Klotz at Discovery Channel.
Thanks. If Michael Meyer is still on the call, you've been kind of quiet. the rest of the conference. You brought up the subject of habitability in your opening comments, and just wanted to follow up on that for a minute. And I know that this isn't really there's not really a clear answer for this, but why is it that you believe that this is evidence that Mars had the right water conditions for the time needed for life to evolve, seeing how we don't really even have that information for how life got started on Earth? Thanks.
So, yeah, I appreciate the question. This is based on the publications that came out in December and then were highlighted in the January issue of Science, which basically looked at Yellowknife Bay and the pH of the water, the low salts in the water, so it's relatively fresh water, water itself, the presence of different oxidation states, all of these things pointing to a very habitable type of environment, one in which, at least as far as we know, Earth microbes may have a perfectly happy time living there. And so in many ways, what I was speaking to is the conclusion from that January issue that at least at one point in time on Mars, from everything that we know, it was habitable. But the big question was, for how long? I mean, if you had water for a very short period of time, would it be sufficient time for any potential life to take advantage of it? At least now, with looking at the size of a lake in Gale Crater and the length of time and series that water was showing up, that implies that there may have been sufficient time for life to get going and thrive. But you make a good point. The information that we have in terms of how long does it take life to start or to originate, and how long does an environment have to be there before life can take advantage of it, these are things that we don't have a very good handle on here on Earth, much less the possibilities on another planet.
And Irene, it's John. Let me just add one bit to that that came up when Eric Hand asked his question. The rocks that we see at Pahrump are only 10 or 15 meters thick. Now that's a lot more than the 1.5 meters of rock of mudstone we had down at Yellowknife Bay. But we're hypothesizing that if this similar kind of rock extends upwards through the rest of the Murray Formation, which is on the order of 150 to 150 meters thick, and that's just the first unit of Mount Sharp. If what we see at Pahrump is applicable to the rest of the Murray Formation, and we get done testing it with the vehicle, that's when you get up to the tens of millions of years time scale. What we're looking at now is on the order probably of tens of thousands to a million years, and that's more than we had down at Yellowknife Bay. But what's out in front of us and still to be tested is where we get really to the longer duration estimates for water being present.
Thank you.
All right, thank you. And we're going to take one last question. A few minutes ago, we asked a question that was allegedly from Emily Lochtawala. It turns out that question actually came from an individual on Ustream, so thank you to that individual for that question. And now I'm going to pose the question that came in from Emily, and this is, again, via social media. So Emily's question is, how has the composition of the rocks changed from delta to the lake bed? Do you want to take a crack at that?
So we don't have enough data to know if it's significant or not, but we have been drilling the rocks as at Yellowknife Bay and then also at Kimberly. And what we noticed, the big difference so far between what we drilled there and what we found at the first hole we drilled in Pahrump was that the hematite concentration went up substantially. There's still magnetite, but there's also hematite there as well. And that was, by the way, something that was predicted from orbit, that the Murray Formation should have some component of hematite. There was also a prediction for some clay, which we saw there as well. And but we're just not going to know until we drill more holes, but that's coming up in the next month or two.
Okay, and on that note, thank you to all our speakers, Michael, Sanjeev, John, and Ashwin, and thanks to everyone who joined us this morning. There will be a replay. The telecon will be archived for 1 week. If you'd like to call 866-396-6287, that's 866-396-6287. And it will also be archived with visuals on Ustream at www.ustream.tv/.